Okay, so having what we've done now, we've done primary alcohols, secondary alcohols, tertiary alcohols, aldehydes, ketones, carboxylic acids. Now, if you're following in the textbook, they just do amines next, but I'm going to jump over to esters, okay? And the reason why I'm going to jump over to esters is because obviously it coincides really well with the esters preparation, which is your summative experiment that we'll be doing in a few weeks down the track. So, esters. We want to look at how we make an ester. Is there any test for esters? You'll find there isn't, okay? But the main thing we look at for esters really is, well, two things. Formation of the ester is big because there's issues that we'll talk about in the practical that you have to resolve. And then we talk about just some simple reactions of esters, and the reactions of esters are not too complex. All right, the general formula for an ester is this. Whenever we look at an ester, okay, you should be able to remember that an ester is made up of two components. And the two components that make up the ester are a carboxylic acid is one, okay, and the other is an alcohol. Now, probably typical for me that I'll put it back to front, but what I'll do is I'll just draw up an ester, and we'll use that one as an example. Alright, if we go right back a few lessons in terms of how we name esters, I said what you need to do is to break the ester in half, but break it here, alright? That's where we want to try and break the ester, and that helps us to work out the structure of the two components that would have made it up, and we'll get to how we make an ester in a minute. So this is the structure for ethanoic acid. That's half of what made the ester, and the other half would have come from this one here, and this is simply methanol. So in order to get to that ester, I would have had to react together two compounds, a primary alcohol in this case, and the ethanoic acid. Matt, watching, all right? Now, the way we name it, the alcohol comes first, so it becomes methyl from the alcohol, and the carboxylic acid next, methyl, ethan, OH is how we name the ester. So it's fairly straightforward, I hope. So let's assume this is the ester that we're going to make. One thing I didn't mention is that esters are noted for their sweet smelling odours, okay, and they are used a lot as artificial tastes as well. So things like raspberries and strawberries and bananas, you associate all those with ester smells. In sector, I've given you a list of some esters and their odours, okay, and similarly there is a list of what we call additives to food. And all those little numbers that you find, I haven't got anything on me at the moment with a number on it, the food item, but if you look at the food items, it will say 105 and 106 added, okay, and they sometimes correspond to esters, synthetic esters. They're not natural flavouring, they're synthetic, all right? So we associate esters with a sweet smelling odour. Now the one that we produce, I think it's supposed to be a banana odour, yeah, that's the one we're trying to aim for.
We did it last week.
Very rarely does it turn out to be exactly how we want it to be, all right? Typically it doesn't turn out like that, it turns out something like nail polish. So we might swap around this year and we'll try a different combination of acid and alcohol and see if we can get a better odour, or something that's much more pleasant. So again, we'll look at that once we get to the experiment. First step, so like we did with everything, how do we make an ester? Well, there is 3 steps to making an ester, okay? The first step is reflux. The second step we haven't talked about before, which is called the extraction process. And the third step is to distill to separate out the product based on its boiling point. So there's 3 steps in the process of forming the ester. All right, there are a few issues with the reaction, so we'll come back to this one. So if I was going to produce methyl ethanoate, I'll write them up on the board in a minute. So if I was going to produce methyl ethanoate, okay, I'm going to start off with, obviously, methanol, and I'm going to start off with the ethanoic acid. Okay, and I'm going to react those together, and the overall equation looks something like this. It's going to produce this ester plus water. Water is a byproduct from that reaction. Now, you'll notice that the reaction is in equilibrium. What does that mean straight away? Going back now, okay, so here's my ester that I've produced. So what does that mean in terms of what we're producing? What sort of a reaction is this? It's an equilibrium reaction. So what it means is that this reaction is going to reverse or go back and produce some of the ethanoic acid and some of the methanol. We can't stop that. Okay, so the reaction is in equilibrium, which means it's reversible. Okay, have that one in the back of your head, all right? The other thing is this reaction is noted for being notoriously slow. Okay, but it actually acid catalyzed that. So the reaction is pretty slow. If I were to speed up any reaction using the theory of collision theory, how do we do that? We increase the temperature. Well, we can't take it any more than the boiling point, but if we were to increase the temperature, we would need to do that and maintain it at a high temperature so it can keep on reacting and reacting and reacting. That's why we have to do a reflux reaction. So we can bump it up there. We're heating it for long periods of time. Our definition of long is maybe 35 or 40 minutes, okay, to improve the yield of the product. From an equilibrium sense, how could I push the equilibrium to the right? There's a few answers to this. Is change of pressure going to impact the system? No, doesn't matter. All right? Now, I haven't given you whether it's an exo or endothermic reaction. If I did, you could talk about temperature, but that's not going to be a huge issue anyway, because we're using temperature. We're going to maximise temperature. All right? What else can we do? Mason? We normally add an excess of one or other of reactant. So that's the first thing we tend to do when we get to our experiment. So it'll be an excess of either the alcohol or the carboxylic acid. Because the more of those things we have on the left-hand side, we're hoping we're forcing equilibrium to the right-hand side. Anyone else see another way we can force equilibrium to the right-hand side? Mason? Okay, is it easy to take the product out? It's not easy to take an ester out as you form it because it's got a fairly high boiling point. What else could you remove? Water. Okay, so just keep that one, all right, in your minds as well, because once we get to the experiment, okay, one of the questions is, how do I improve the yield of the ester? Well, anything that forces equilibrium to the right, when I'm making an ester, is going to improve the yield. So there is a piece of apparatus that you'll look up on the internet, okay, called a apparatus, all right? Apparatus, all right? And I don't want to give the answer because it's your practical and you need to find it yourself, okay? So there is a piece of apparatus where you can do this, okay, under reflux conditions and actually remove the water. We don't have that apparatus to use here, okay? Most schools have got a straight, quick fit set, okay? We are lucky we've got the heating mantle, so that helps us. So, in terms of the steps that we're going to use to produce the ester, the first step is obviously reflux, all right? So what we're going to do is, and we'll do it for our simulation, we're going to have our flask that's sitting in a heating mantle, all right? And, because we're lucky, and we are going to heat that system for around about, depending how we go, 1 to 2 hours. No, we're not. We'd like to do it for 1 to 2 hours. We might get it for about 40 minutes. What we're going to do though is we're going to mix together our acid, that is our concentrated sulfuric, that is the reagent that we use, it's a catalyst. Our carboxylic acid and our alcohol, we're going to mix it together the night before, okay, and let it stand overnight, because the reaction will actually start even though we're not heating it. Alright, so we're going to let it sit for 24 hours prior to doing reflux. Alright, when you do the reflux, you'll be asked to do some observations. What do you see when you mix the chemicals together? What do you see during reflux? And what do you see after 45 minutes when you've done the actual reflux? And you might see things like colour changes. By the time it gets to the end, you will definitely, you should, in the flask, end up seeing definitely 2 layers, okay, in the flask. That becomes fairly visible towards the end of the reaction. One of those is the ester, because the ester is insoluble, okay, in the aqueous solution. Alright, it can't H-bond with water, which is a bit of an advantage. Alright, now, so what we do is this, we reflux, then we carry out a process of extraction. Extraction, you can basically put behind that the word separation. What we want to do is try and separate out the ester, okay, from everything else in the mixture. So this is where we set up, okay, this is called a separating funnel, and some of them different shapes. Put our chemicals in, okay, and the first step to extraction is we add water, and the procedure says add about 20 mils of water. So here, I transfer, okay, my mixture into my separating funnel, and I add water. And then I'm going to shake it, and you've got to be careful because sometimes it creates bubbles, alright? And then I take this, you don't have to have 2 flasks actually, because I think the top one works out to be the ester, but don't quote me on that one. Do you know how to work out which one is the organic layer? No, it's not easy. If I put water in here, what you'll probably find is the water will go straight through and the water will just go to the bottom. It's not, you know, that's how they do lava lamps, right? It's a mixture of like an organic solvent and just water. So if you add water to this, I think you'll find that the water will go to the bottom. Okay? So we take off what we call the aqueous layer. Okay? And you can take the organic layer off, but I tend to leave it in the flask. Okay? So this is the stuff that we're after here. That will be my ester, and I'm going to leave that in the flask. Because the more times you take it in and out of the flask, the more that you lose your product. And I didn't mention right at the beginning, but you'll be weighing your compounds, your starting materials at the start, because you've got to work out the yield at the end. Alright? So then I do that. Okay, then what I do is, so I've done an extraction or a separation with water. Okay, what's going to happen with the water? What things will dissolve in the water? Because we want to try and separate things out as much as we can. So maybe any unreacted methanol will dissolve in the water. So we got rid of unreacted methanol. Okay? Maybe some unreacted ethanoic acid will dissolve in the water. You have to do equations for these reactions, by the way. You've got to show that these actually are going to react with the water layer. And maybe some unreacted sulfuric acid, we want to try and get that out of the solution as well. Okay? So we do the ester, we just wash it with water, we call it washing, okay, with water, and we try and get rid of some of the compounds in step 1 of the extraction. Step 2, oops, my funnel has grown in size, doesn't really matter. So here is my organic layer here, again, and in step 2, I'm adding a solution, it doesn't really matter, of sodium carbonate or sodium bicarbonate, either one of those, doesn't matter. Okay? You'll be given some salt and you make up your own solution. So then the issue with this though is that we get lots of bubbles of carbon dioxide, and this one here you've got to be really careful. So when you stop at the top of the flask and you shake it, it's going to like, you really hear it. It's like opening a Coke, alright? or a beer, all right? So basically you've got to be careful with that one. So this is a definite indicator that there is acid present, and then we take the aqueous layer off, okay, and we make sure it's the aqueous layer. Don't throw anything away, because some people get confused and they take the aqueous layer and they tip it down. You won't put it in the sink because it will stink the lab out for days after. You'll put it into the fume hood, okay, into the disposal jar that we've got there, and some people throw their product out. We don't want to do that because we won't have time to do the experiment all over again. So you're just going to make sure that the aqueous layer is the one you're carrying through. Alright, the next step is you simply then take your organic compound. It tends to go into a conical flask that you stopper, and into that conical flask you add calcium chloride, which is, we call it fuse, but it's anhydrous calcium chloride. Now the anhydrous calcium chloride sits in the bottom of the flask and it's like a sponge. It actually sucks up all the moisture. Alright? So we end up with, at this particular point, we're ending up with, hopefully, we've sort of extracted everything else. We've got rid of all the acid, all the unreacted alcohol, we've got rid of everything. The only thing we haven't got rid of is water. So then we use the calcium chloride to extract the water. Okay? The last step is we carry out, and then we set up for our process again, and I'll just modify this diagram over here to save a bit of time. And so the last step, okay, is we set up for our distillation, okay, and we know, because we've actually looked it up this particular point, we know exactly the boiling point of the ester. And so the last part is we take that compound, we decant it off, we just pour it off, okay, into our round bottom flask for our heating mantle. We know the boiling point for the ester. We then do a final step is distill the ester off. Now this is the important part, because you'll be observing the colour, you'll be observing the odour of the ester, and it'll be fairly obvious, okay, when you get these fractions. And of course we're going to have other possible things that will come through. There's possible there could be some acid in here, some sulfuric acid, boiling point about 300 or something. There could be some methanol that's gone through still, even though we tried to do an extraction. Okay, so there are possible contamination. We would get the ester, boiling point's about 128 from memory of this one. Might be fraction 3. In a perfect world, we take that, we redistill it again. Okay, but some people also forget as a step, you've got to weigh your product or record the volume of your product. You can use essentially to work out the mass, because you want to work out the yield. The best yield I've ever seen for this experiment is about somewhere between 30 to 40% maximum, even if you've been at reflux for days. So you can't achieve much more than that. Okay, not with the system that we are using. So people that come up with like 80% yield are obviously fudging their results, so don't even try. So that process of reflux, extraction, drying, distillation, okay, is fundamental in the production of your ester. Is there a chemical test for an ester? The answer is no. There's no chemical test for an ester. Okay? We can use the idea of the odour, but it's not 100% accurate all the time. So don't assume you can do that. All right, thanks guys.